see, here we go. Okay, so it is my very great pleasure to introduce our first seminar speaker for this year's, the third year of the Mathematical Laws of Morphology and Biomechanics Seminar Series. Dr. Kiisa Nishikawa is a Regents Professor in the Department of Biological Sciences at Northern Arizona University. She received her Ph.D. in zoology from the University of North Carolina, Chapel Hill, and her lab focuses on questions related to molecular muscle physiology, kinesiology, biomechanics, neurophysiology, and exercise science. In particular, Professor Nishikawa's lab focuses on understanding the variation in muscle force during active muscle length changes and the molecular structure and function of titin and ways to apply that work to control mechanisms and algorithms for prosthetic devices. So we're very excited and honored to have Professor Nishikawa coming and speaking with us today virtually. So please take it away.
Well, thank you so much. It's really a pleasure to share my research with you, and I thanks so much for joining. And we're such a small group that, feel free to interrupt as we go along if you have questions. Today what I want to talk about is mathematical laws of muscle mechanics and how I really want to convince you, I think most of all, now the screen isn't advancing, oh, there we go, that we really need some new laws. The old ones are perfectly good for what they are, but if we really want to predict in vivo muscle forces, we need some new ones. And so the next generation of muscle scientists has to help us figure that out. So I just always start by thanking everybody who's contributed to this project over the years. So some undergraduate students did quite a lot of the modeling. Current graduate students, Caitlin Bemis, Sue Zhang, and Nicole Rice have really contributed to the data I'm going to show you today. I have a great team of collaborators, including Monica Daly, Jill McNick-Gray, Ann Silverman, Simon Sponberg, and Madhu Venkadesan, and they've really helped to develop the ideas that I'm going to present, and of course financial support from NSF, Northern Arizona University, and the Keck Foundation. So this is a really quick outline of what I want to talk about today. I want to talk about, the two of the most famous long-term laws of muscle mechanics, the isometric force-length relationship and the isotonic force-velocity relationship. And I want to talk about their strengths and limitations. And then and really convince you that there's a knowledge gap between sort of the top-down approach to muscle mechanics, where we look at organisms moving and we measure things while they're moving, and the bottom-up approach, where we take muscles or muscle fibers or single molecules from muscle sarcomeres in a dish and then measure the mechanics under those conditions, and then try and fill in a complete theory from one end to the other. So there's this knowledge gap between, top-down and bottom-up approaches, and I want to tell you about some experiments and models that demonstrate this gap. And I'm going to use an example from Simon Sponberg's research on cockroach leg muscles and Monica Daly's research on in vivo guinea fowl leg muscles to try and convince you that this gap exists and is pretty important. And then I'm going to talk about some models and data that may suggest the beginnings of a new framework for some dynamic laws of muscle mechanics. And this involves some concepts as like muscle is, rather than a motor, is a tunable active material. So when muscles are activated, their response to forces that deform them changes. And it seems like that's a pretty important, new paradigm that might help us bridge this gap. I also want to talk about different ways of thinking about the length effects and velocity effects on muscle force. So let's get started and have a little history lesson here. So the isometric force-length relationship is very long known. The canonical historical paper was by Al Gordon and Andrew Huxley et al. In 1966. And basically what they did was they took single fibers of muscles, they measured the sarcomere length, So the striation spacing is here on the x-axis, and they measured that the tension that the muscle fibers could produce at different lengths. And it's really important to go back and remember how they do this. So they actually take a muscle and they stretch it passively to a particular length, activate it, measure the force, stretch the muscle, deactivate it, stretch the muscle to a new length, activate it, measure the force, deactivate it, stretch the muscle, etc. So this is strictly isometric. The muscles aren't moving, and it's not it's not measured continuously, right? It's a very discrete, non-continuous estimate of the muscle force at different lengths. And of course, what's really important and what was historically important about this law is that it really fit with the sliding filament theory. And believe it or not, back in the 1940s, the sliding filament theory was extremely controversial. Both biophysicists and biochemists didn't believe it. They said filament sliding past each other, generating force. We don't have any models for that. There's some really interesting historical accounts of Jean Hansen standing up at a meeting and waving her arms and saying, "I don't know how they slide, I just know they do it." So this was really historically important to show that the forces produced by muscles beyond overlap of the thick and thin filaments is very small, that the linear sort of increase as we go up the descending limb in muscle force is consistent with increasing overlap of the thick and thin filaments. And so historically, this was extremely important in supporting, right, the sliding filament theory. And this is actually a quote from Gordon et al. Paper. Many features of this length-tension relation are simply explained on the sliding filament theory. And so, of course, we have this canonical sliding filament theory putting together these nice little pictures of thick and thin filament overlap along the isometric length tension curve. But we know that there's limitations, right? So we know that when we dynamically change the length of active muscles, we don't see this relationship. So these are some data from a paper by Walter Herzog. And so what happens is that they start at a shorter length below some reference length, activate the muscle and stretch it to, right, activate the muscle and stretch it to some reference length. Or if we dynamically start at a longer length and shorten the muscle to some reference length, then what we see is that there's a dynamic response of the muscle that settles down into a more steady state. And both with stretching and with shortening, the final force of the muscle is not what we'd expect from the isometric length tension curve. So already we're seeing that it's difficult to apply these measures made under isometric conditions to dynamic length changes of muscle. So how about the isotonic force velocity relationship? So again, I think it historically extremely important, and I'll go into some detail on why that is. But again, it's a very discontinuous type of measurement. So what we do Hill invented this experiment, back in the 1930s. What did he do? He starts with a muscle, he activates it, and when it reaches a particular load, he just lets it shorten against that constant load over time. So you can see, and then you deactivate the muscle, go back, reactivate the muscle, let it shorten at a different constant load, and so on, to create this, again, fundamentally discontinuous, discrete measurements. And from these afterloaded isovelocity shortening, isotonic shortening experiments, this is the muscle force, which is constant, or stress, which is force divided by the cross-sectional area. And here we see the corresponding length changes. And so in order to construct a force velocity curve, what we actually do is we measure the linear initial rate of shortening and plot that rate of shortening as a function of the load. So what we inevitably find, and this is true of all motors, whether it's a copper coil that you made from a kit at home, or a muscle, is that we see that there's some um, load at which the velocity is zero, and there's some velocity at which the load is zero, right? So unloaded shortening velocity is going to be the fastest velocity that muscles can do under isotonic conditions or constant force conditions, and there's going to be some stall uh, load as well. So in terms of the historical development, A.V. Hill in 1938 realized, as I just said, all motors have this force velocity trade-off. And in 1938, Hill's classic paper tied the force velocity relationship to muscle energetics, right? So he actually measured this force velocity curve. He came up with this equation, which is a rectangular hyperbola that relates the speed to the load in isotonic, that's constant load shortening. And he also derived a similar relationship for the heat liberated by muscles during shortening. So he had this very similar equation, right, for the energetics. And what he observed in 1938 was that the constant A of muscle mechanics and the constant alpha of muscle energetics were approximately the same, as and also true for the constant B and beta, right? And so, the big take-home message of A.V. Hill's famous paper is that we have an internally consistent theory of muscle mechanics and energetics. And in 1957, one of the really brilliant insights of Andrew Huxley is that you could explain muscle mechanics and energetics with a two-state cross-bridge model. Okay, so the cross bridges can either be on or off, right? So the on rate, you have an on rate F and an off rate G, which are influenced by the strain in the cross bridges, right? As they perform their power stroke and go through a cross bridge cycle. And this two-state cross-bridge model was consistent with Hill's energetics equation. So it's 1957 and everything adds up. We have this beautiful internally consistent theory. And we've gone, we have the sliding filament theory, and now we have this cross-bridge theory, right, that's consistent with the sliding filaments. But in 1964, and this is kind of like the little known part of the history, or the somewhat forgotten history, Hill's very last paper revised his heat measurements, breaking the link to the cross-bridge model. And these are kind of long quotes, and I apologize for them, but I think they're just too interesting not to share with you. So the original conclusion that A and alpha were the same was probably due to a persistent error in the measurement of alpha, making it about 30% too great. So Hill broke his own symmetry between muscle mechanics and energetics, but he also knew about Huxley's model. Remember, that's in 1957, and he specifically calls out to Huxley in this way. He says, in the discussion of energetics in his sliding filament theory, and parentheses, crawling filament might be a more vivid description. Huxley in 1957 made various calculations of the heat and total energy as related to load and speed. He compared the results with quantities calculated from my earlier findings. Since it is now known that the constant alpha of the heat of shortening is not the same thing as the A constant of the characteristic equation, but rather depends on the load, it would be interesting to repeat these calculations with the new facts in mind. So now it's 1973, and Huxley comes back with his three-state cross-bridge model, right, which very nicely fits the revised energetic measurements. So now we have not only bound and unbound cross-bridges, but the bound cross-bridges can be either weakly attached or strongly attached, right? And the model nicely fits the data, but is consistent now neither with the force velocity, but now neither the cross-bridge model nor Hill's revised energetics measurements are consistent with the muscle mechanics and the force velocity relationship. And that all of those things remain true today. So just like the force length relationship was important for supporting the force, the sliding filament theory, the force velocity relationship has been extremely important for supporting the cross bridge theory. But we also find limitations in the force velocity relationship. And this is just one illustration here from the work of Taya Finney. And so this is actually from humans doing sort of squat-like movements on a dynamometer. And so these are the quadriceps muscles, and what happens is that during sort of knee flexion and extension movements, you can generate a work loop. And so, and in this work loop, you have, time varying force and velocity. And what you can see, and this is the muscle tendon unit velocity here on the X, and the patellar tendon force on the Y. And what you can see is that actually in vivo, the quadriceps muscles do a lot better than the force velocity relationship would indicate. And so Uzma here in my lab did an interesting experiment, and this was on ex vivo mouse muscles. And what she actually did was a series of work loops. And these are kind of odd work loops in that activation is constant. So the muscles are just continuously active during the loops. And she just used the same frequency, but a larger and larger amplitude of the length changes. And so what she did is whenever the muscle crossed L0, she measured the velocity and the force, and from that she was able to construct a force velocity relationship. And what she found ex vivo is very similar to what Taya Finney found in the human quadriceps, is that in work loops, right, which are not isotonic, they have a continuously varying load on the muscle, that you see that in fact that for a given velocity, the force produced is much higher than you'd expect by the isotonic force velocity relationship alone. So, so we know very well these spatial hierarchies of muscle, all the way from the single molecules up to the muscle, and even up to whole organisms, right? And there's also temporal and control hierarchies, going all the way from intrinsic muscle properties, which respond nearly instantaneously to changes in load in both passive and active muscles, and action potentials, which are on the order of a few milliseconds, all the way up to, strides, locomotor bouts, etc. And we also have these control hierarchies, right? Muscle intrinsic properties, reflexes, which operate on slower time scales, and cognitive effects on movement, and anticipatory adaptations of control over even longer time periods. So we have these different hierarchies, and the force length and force velocity relationships, while they're historically important and were consistent with the sliding filament and swinging cross-bridge theories, they really fail to predict force in dynamic movements. And that's what creates this knowledge gap between in vivo measurements of force in dynamic movements and the predictions of these theories. So what the real purpose of my seminar today is, to try and start to answer this question: how can we develop predictive models and theories that for dynamic muscle function? So that brings us to the examples. So, so I want to talk in some detail about this experiment, this very clever experiment that Simon Sponberg did. And so it's a in situ experiment. So we have the whole cockroach, and the muscles is being perfused by the cockroach circulatory system. But the cockroach is immobilized, and so what we can do is we can attach the muscle to the arm of a force transducer. We can stimulate the muscle using electric shocks, and so we can use this in situ preparation to try and understand dynamic muscle function. So here's the really killer, experimental design that Simon had. So he varied the frequency of work loops of this cockroach leg muscle, and he also varied the amplitude, and he varied the frequency and amplitude together so that the muscle length and velocity is always the same at this point in time. Then he did a perturbation, a stretching perturbation of the muscle that's always the same amplitude and duration. And so the idea is that if the isotonic and isometric laws apply, then this muscle should produce the same exact force in response to the perturbations, right? Because its length is the same and its velocity is the same at this point in time. But of course, what he found is that the force during and after the perturbations was quite different, showing that these laws don't apply to dynamic force production of muscle while the length is changing. And so he actually made this interesting observation about what he called the preload. So the preload is actually the force. So already the forces of the muscles, and the gray bar shows activation. So the activation and the perturbation come at exactly the same time. And so what Simon noticed is that already before the activation and the perturbation come, there's already a slight difference in force, which Simon called the preload. And it turned out that the relative stress of the preload was a very good predictor of the relative work that the muscle did during the perturbation. So these perturbation experiments reveal these history-dependent effects of preload. So Simon made this little model, a pretty simple model with like 3 parameters. And the idea is that there's a contractile unit, there's a spring and a damper in parallel connected to that contractile unit. And the contractile unit has this property of it has an equilibrium or a zero force rest length. And the idea is that the difference in the preload is that the muscle is displaced by some delta x, right, from its equilibrium position. And so the model with all 3 of these parameters, the preload, the stiffness, and the damping, did a really, really good job of predicting the actual work during these work loops. But note that the damping and the stiffness individually were terrible, right, at predicting the relationship, and only the preload, right, which is a function of this displacement from the muscle equilibrium position, showed a significant ability to predict the actual work during the perturbed work loops. So my student, Siwoo, took these data, and he actually made 2 models. So now we have to talk a little bit about models. A Hill type model, and we're going to also talk about a Titin inspired model. And so and I want to spend a little bit of time talking about Hill type models because I feel like there's a lot of confusion out there about them. So Hill type models have not only a force length and a force velocity relationship, and sometimes also tendon dynamics, but they also have an activation dynamics module. And typically in the simplest Hill type models, the activation dynamics has 4 parameters. So an activation factor, which you can think of as a scaling, right? So it scales, for example, the EMG to force. There's also a delay due to excitation contraction coupling. So that's the delay, for example, between when you stimulate a muscle and when it starts to develop force. There's an activation time constant that models how fast the muscle reaches its peak force, and a deactivation constant that models how fast the force decays. And typically the deactivation time is much longer, like 2 to 3 times longer than the activation. And this is for like a first order model of the activation dynamics. But recently, Taylor Dick and James Wakeling have published second order and third order Hill models. And in this case, like the second order goes not only on the rise rate, but the rate of the rise rate. And then the third order would be the rate of the rise rate. So you can get up to 8 free parameters just in the activation dynamics alone. Then we have the muscle mechanics part. Oftentimes, because of so many experiments since Hill, all the parameters are known and none of the parameters are free. But typically, we have an optimal length and maximal isometric force, which are measured experimentally. We have a passive force length relationship that's typically an exponential with 2 parameters, an isometric force length relationship with 3 parameters, and an isotonic force velocity relationship with 2 parameters. So Siwoo coded this in MATLAB. Oh, I guess, and so I'll tell you about the other model, and then we'll model Simon's cockroach data using both of the models. So here's this Titin-inspired model, which Andy Ruina, who I noticed is going to be a speaker later in your series, helped me to develop. And it's very similar to the Hill model. It's got and also to Simon's little toy model that he made, right? It's got a damper and a spring in parallel on one side of a pulley, and it's got a contractile element and a damper on the other side of the pulley. And then it's got a series elastic element that's you could think of as a tendon. So the force in the series elastic element is the same as the force of this contractile element and Titin-like spring in series. But the cool thing that seems to be really useful in modeling muscle force is this pulley. So the idea is that, in muscle sarcomeres, the pulley would represent thin filaments and the titin wraps around the pulley. And the idea is that the contractile element turns the pulley in the counterclockwise direction, which creates a change in the equilibrium length of the titin spring. But if I apply forces to the muscle, that translates the pulley. Right? So if I push on the muscle will shorten. If I pull on the muscle will stretch. And so this pulley is a useful thing. I got a little ahead of myself here. So the contractile element is, very similar to the contractile element in Hill models. And it rotates the pulley counterclockwise. The forces on either side of the pulley are balanced, right? And they each produce half of the force that's experienced by the series elastic element. And the model has, so if we count up, so the Hill model had anywhere between 13 parameters and 17 parameters. This model has 10 parameters, 5 of them are free, so we have the same for a first order Hill model, the activation time constant and the act factor. And then we measure the isometric force and the optimal length, but then we have these, the muscle mass, which is typically measured, and 3 free parameters for the damping of the CE, the stiffness and damping of the titin, and the SE stiffness. And one feature of this model, which I don't have time to demonstrate for you, but I'm just going to tell you, is that this model does reproduce the isotonic force velocity relationship without hard coding, so long as the conditions are actually isotonic. So now we get to the point where Siwu used this model to predict the data from Simon's cockroach leg muscles. And as we predicted, so he had 4 conditions. So he had eccentric and concentric, eccentric in blue, concentric in red, and he had active muscles and passive muscles with no activation. So the open symbols are the active and the closed symbols are the passive. And as we predicted, because the length and velocity are always the same in all the trials, the force predicted by the Hill model is always the same for both the passive and the active. But the nice thing was that the Titin-inspired model actually did a much better job of predicting the differences in peak muscle force and work per cycle compared to the Hill model. Okay, so example number 2. So now we're starting to see that, these historic laws of muscle mechanics were really important in their time, but they don't really relate to in vivo dynamic muscle force production. So Monica Daly over the years has, her lab has really been a leader in designing perturbed experiments to measure dynamic muscle function in vivo. So she does these really amazing implantations of various sensors in live animals, including sonomicrometry crystals in the muscle fascicles, which allow us to measure the change in muscle fascicle length over time, tendon force buckles, which allow us to measure the muscle force, and EMG to measure the muscle activity. And so this just shows one of her early experiments where a guinea fowl running on a treadmill steps into a hole, or a platform, I guess, steps into this unexpected hole that it doesn't see. And the birds are amazingly robust to these kinds of perturbations. Like, they almost never fall down. And so during these experiments, she's measuring the dynamic muscle function. So what you can see is that the length of the muscle fascicles is almost identical during level steps, which are in gray, and this pothole step in red, until the leg goes through the paper, right? And all of a sudden, the length excursion of the muscle is much greater when the bird falls into the pothole. The force that the muscle produces is much less, and you can think of it acting as a shock absorber, right? But look at the activation of the muscle. It's actually greater during the pothole step. So now we have this dissonance, right? Perturbations reveal that the neural control and the muscle response is uncoupled. So what's going on? It should be something to do with the changes in muscle length and maybe muscle as a tunable material. So Monica did another series of experiments, and we've really spent quite a lot of time modeling these experiments in various ways. And in this experiment, instead of stepping in a hole, the bird is running on a treadmill, and these obstacles come they're of various heights, and they come at various phases of the gait cycle of the instrumented leg. And so, and what you can see is, like, here's a step up. And so what happens is the bird's foot hits the obstacle. It changes the length profile of the muscle. In this particular stride, the EMG is potentiated and the force is very high. Here's a different stride from the same trial, and I'll show you the whole trial in a minute. You can see actually here the bird kind of falls down with the instrumented leg off the obstacle. Similar to falling in the hole, the foot hits the ground about here. But here we can see, once again, we can have a really potentiated EMG. So the bird says, uh-oh, here comes an obstacle. A lot of muscle activation, but very low force. And so this is just a work loops showing all 62 or however many strides of the instrumented leg in one for one bird on the treadmill in one whole trial. And so the way these go is counterclockwise. So the muscle's passively stretched. It's activated about here. The muscle shortens and the force rises approximately at the time when the foot hits the ground. So all of these big forces up here are steps up onto the obstacle. And then these sort of vaguely L-shaped work loops are for level stepping, and filling in this hole here are the steps down. And I think it's really important to notice that the work per cycle can be 40 times less when the bird steps down than when the bird steps up, although the EMG can even be more in the steps down than in the steps up. And this just shows, again, all the trials. So you can see, you can pick out the obstacle steps. They've always got some perturbations in the length. They often have higher than average EMG. And you can see they sometimes have much higher or much lower forces, depending on whether the bird is stepping up or down from the obstacle with the instrumented leg. But here's what we see is that these red ones are all steps up onto the obstacle from the treadmill, and these ones are steps down. And again, you can have a perfectly average step up with a higher force, or you can have a big EMG with a higher force. You can have a big EMG with a lower force, or you can have an average EMG with a lower force. So just again, more uncoupling. And the last aspect of the data that I think is really interesting is we line up all the strides based on where the EMG starts, and then we look at where does muscle force develop. And it turns out that you can measure excitation contraction coupling delay of about 25 milliseconds in these birds. And you can see that there's some activation of there, right, of some of the muscles, but sometimes the muscles take like up to 125 milliseconds. And there's a huge variability. So there's no demonstrable canonical excitation contraction coupling delay in these muscles. And so one of the things that we did was we said, okay, let's take these data from the in vivo guinea fowl and let's just play the data onto an ex vivo mouse EDL muscle and see what happens. And so we stimulated at submaximal voltage. We began and ended the stimulation at lengths approximating the in vivo guinea fowl muscle. And we used strain inputs from different guinea fowl steps at constant activation of frequency. And so the reason for doing these experiments is like you never can step in the same river twice, but you can never even take the same step on a treadmill twice. So in vivo, everything's varying all at the same time. And so if we bring these into the ex vivo world, we can precisely control the strain and activation. And so here are the guinea fowl data. Here are what you see here is like the strain and activation for both the guinea fowl and the mouse muscles, right? And actually the black line here is a purely sinusoidal length input at the same amplitude and frequency and the same activation. So activated at approximately the same length, deactivated at approximately the same length. And here are the force traces. So here's the muscle passively lengthening, it gets to its longest length and it starts to shorten, and here's where we activate it. And you can see that the time of the peak force and the delay between activation and peak force are really nicely replicated by these in vivo, by these ex vivo experiments, right? And so we get these length-dependent EC coupling delays that we actually see in the bird in these experiments as well. And so this motivated Siwoo to do this, to try and create similar, Sorry, got my cat in. This is the problem with working from home. Similar experiments, and I think this is really important. So the muscle is passively stretched. These are all ex vivo, right? And then we're going to stimulate it, and it's going to actively shorten. And then we're going to produce these perturbations that are somewhat similar to the perturbations that Simon did, and somewhat similar to the actual in vivo guinea fowl. So what happens when the foot hits the ground, right? When the foot hits the obstacle, is the velocity goes from some value to zero or close to zero in a very short period of time. So notice that there's no stretching, there's no eccentric contractions. We're just gonna decelerate this muscle during active shortening, and this is what we see. So when we decelerate the muscle, we get this big increase in muscle force, just like Simon got during his stretch perturbations. And so this is motivating a dynamic law of muscle force that's based on time varying load. So if we can load a muscle just enough, or we can load a muscle that's shortening enough to slow it down, we can load it enough to bring its velocity to zero, or we can load it enough to stretch it. And there should be a dynamic force velocity law that we don't know what it is yet that should predict the muscle force. And it should be continuous. We can throw away this really unsatisfying, discontinuous thing where we have a different equation. We have to write a different equation for all the different um, velocities that a muscle can experience in a dynamic contraction. So we're working on this, but we need help. We can't do it all by ourselves. So now I think I have about 5 minutes maybe before questions. So I just want to end by now we're going to apply the Hill model, and I'm going to go through this pretty fast, and the Titin model to Monica's data. So these are just the in vivo data. We've also done some modeling of the EDL data. And so here's the Hill model. So we're walking, slow walking, 8 meters per second, no obstacles. And with a third order model that has 8 free parameters, we can get a really big R squared, like 0.8. And you can see actually that that some features are missing. So what are the limitations here? Well, the strengths, high overall R squared. Good prediction of the force rise and of the force onset and rise rate. So these are really good. They're spot on. But pretty much everything else is not so great. So first of all, we have to really filter the velocity input to get such a good fit. We aren't catching the viscous component of the passive force at all. We have a passive force length relationship, but it's like purely elastic, right? And so nothing there. And it's a very poor prediction of the force decay, right? And that's all due to the force velocity relationship debiting the force too much. And I'm going to skip over this in the interest of time, but basically if you optimize on the activation dynamics on one stride, then it does very poorly on other strides. So the one big problem, and I'm going to skip over this too, but one big problem, so here we're just looking at twitch force, titanic force, and potentiated force if we give 2 twitches in close succession. And the point of this work by C.J. Heckman and Tom Sandercock is that the force rise rate depends, this is isometric, this is shortening, this is lengthening. It completely changes if the muscle isn't isometric. But this isn't at all captured by even like the third order activation dynamics of the Hill models. So here's the Titin model, right? And it has the same inputs and an even higher R squared. It has a good prediction of the passive force and a good prediction of both the rise and the fall rate of the force. And what's the major limitation is like we don't have decades of experiments to measure the parameters. So we need new experiments so that we can routinely measure the parameters for this model in vivo. And one of the interesting things about the model, so this is just the purely model data, and it shows you like the internal parameters. So the blue is the force of the contractile element. The yellow is just linear damping, and the purple is the actual muscle force. So in general, the biggest problem with modeling muscle data is that there's this delay between activation and force, and linear damping does a really rather nice job of fixing that problem. Oops. Okay, so now we are going to compare the Titin model to the Hill model. We're going to do a better experiment where we train on one data set. We train all the parameters on one data set, and then we test on another data set. So we're going to train on walking, and then we're going to test on walking at the same speed, but with these treadmill obstacles. And we can see that we get really high R-squareds for both models on the training set. Both models show overfitting in that the R-squared value decreases in the testing, but it decreases like a lot more for the Hill model than for the Titin-inspired model. And when the activation is big, or when the activation is big, the Hill model predicts a big force for the obstacle strides, but when the activation is average, the Hill model doesn't catch that, but the Titin model does. And then this is like my very last thing, and then I'm going to wrap up. But Anne Colewine very recently, in collaboration with Monica, modeled the exact same data set. How cool is that? And she used 1, 2, 3, 4, 5, 6 different Hill models and AI machine learning convoluted neural network model. And this Thielen model is the one that's used in OpenSim, and it had the lowest R squared. Hart McGuire and Hugh Herr's model and Friedel de Groote's model were about the same. And then, these other Wakeling, Esposito, Colewine, Hill versions were all about the same. But none of them did as well as the Titin-inspired model. So there's something there. You don't have to believe that actin is a pulley and sarcomeres, but there's something there that has predictive value. So I'm just sorry to do this, skip over, but I think I'll just really end and say, we need a new framework to bridge the gap and really develop predictive muscles of dynamic muscle mechanics. And I think that this idea of muscle as a tunable material where activation and dynamic length changes or intrinsic muscle properties that are tuned by activation interact in the production of muscle force. We need new experiments. We think perturbations are the secret sauce. We think that, so the idea is that the experiments that we do at the front using the bottom-up approach need to be informative of in vivo muscle function. We need new parameters. We need maybe something like equilibrium length and preload. And we need to start thinking about replacing the isometric force velocity relationship with a new law, replacing the isotonic force velocity relationship with a new law. It should be a continuous function of time varying load. And we need to, so we should be able to predict the length dependent activation dynamics as well as the perturbation response. So we're working on different ways to do this, but I'm going to stop and I'd be happy to answer any of your questions.
Thanks so much, Kiisa. That was fantastic. Does anyone have any questions?
So I have a question. In your model, how do you compare the models? Because they have different numbers of parameters.
Yes. Yeah. So maybe can I go? Let's see if I can go back. Yeah. Unfortunately, I don't seem to be able to go back. Oh, here. Now I'm going back. Okay. I did have a slide on comparing the models. So because they do have different parameters, and so in the particular models that we use, we have 8 free parameters for the Hill model, and those are all in the activation dynamics. And we have 5 free parameters for the Titin inspired model. So, and we use we use R squared, RMSE, which is like sort of the total error, Akaike information criterion, and the Bayesian information criterion. And so, if the model that does worse has more parameters, these debit the fit on how many free parameters there are. And so that the Hill model is only going to do even worse when you take into account the number of free parameters. But what I found from doing that is that it's really kind of surprising how little the debit functions are. Like they're really, really not very big. So I think they work okay. They were designed for more regression models, and I think they work okay for regression models, but I don't think they work as well for this type of model.
Yeah, I kind of agree with that. Like, I would have tried at least something like just a split on between like training and validation at least, so to see if there is something there, because these are somehow that. So AC and BAC R square, it doesn't work for models with different variables. Of course, it gives advantage to models with extra variables, and similar for RMSE. Then, of course, AIC and BAC, it's true that they take consideration different number of variables, but they are somehow they are based on hypotheses which are practice never verified. So so that's I agree with that assessment.
Yeah. So I think there's still some theoretical work to be done on how you really compare models that don't have the same fundamental structure. But then you can also compare them using, this training and testing, and this is so seldom done in muscle modeling, and it's really, really important. And the trick of the perturbations, why there's such a good experiment, is because it's really, 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 really easy to overfit constant speed, treadmill, walking, or running, because every step, there's no step-to-step variability. So we need to really be thinking about overfitting. And then this last one I just didn't have time to say anything about, but it's really important to me. And it's like this modularity. So the Hill models are modular. The Titan model is modular. We need to we can test one at a time how good the modules do it. Do they make the fit better, or do they make the fit worse? And so in the Hill, so far as I know, I'm the first person to do this, but I took like the 8 parameter third order Hill model, and I took the muscle mechanics out, and I trained the activation dynamics on the data without the muscle mechanics, and the fit was better. And then I did a similar thing. Well, Siwoo did it really. Siwoo took the pulley out of the Titan model, and the doesn't work anymore. So, it basically is very similar to a hill model. So I think we really need to, not just assume that the modules that we throw into our model on first principles are really helping the fit.
Yeah, I think that's a really good point. And it's the scary thing about modeling, I think, for the experimentalists is the, you know, arbitrary. I mean, it's not arbitrary, right? But these things that we put in there, that trying to understand their contribution to the models and how close or how much do they resemble the actual, reality. And are they helping us understand these fundamental principles, or clouding the issue, or just filler, not having any impact whatsoever in one way or the other? So, yeah. That's a very good point. I think we're gonna have to cut it off. But perhaps if other people have questions, they might be able to email you. Is
Oh,
that all right?
absolutely.
Yeah.
Please do.
Yeah, that was absolutely fantastic. Thank you so much,
Oh,
Kiisa, for joining us and for taking the time to speak with us. This was a really fascinating talk.
well, thanks so much. And I'd love to get your feedback too, because I am an empiricist and not a modeler. So, yeah, so if you have feedback or questions, I'd love to hear from you. And my email is just first name dot last name at nau.edu.
Great. Thank you so much,
Okay.
Kiisa.
Yeah. Thank you for inviting me.
Our pleasure.